Welcome to Ultimate Sleep Doctor. Tonight, we journey into a vast and ancient story. From the faintest glimmer of light to the grand dance of galaxies, we'll explore the unfolding tale of the universe. It's a story of creation, expansion, and the slow, beautiful evolution of everything we know. Consider the immense scale of it all, a silent, unfolding drama played out over billions of years. There's a profound comfort in knowing we are part of this extraordinary unfolding. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe. Let your thoughts drift. Let's begin. The very first moments of the universe weren't like anything we experience today. It wasn't a sudden flash of light, though that's how we often picture the Big Bang. Instead, it was an incredibly dense, incredibly hot, and unbelievably chaotic era, a period so far removed from our current reality it's hard for us to truly grasp. We're talking about a time before atoms, before stars, before galaxies, a time when the fundamental building blocks of everything were swirling together in a soup of unimaginable energy and density. This initial phase, occurring fractions of a second after the Big Bang, is a subject of intense investigation for cosmologists, and it's often referred to as the primordial soup. Our current understanding of the Big Bang suggests that immediately after the event, the universe was not expanding smoothly. Instead, it was filled with a state known as quark-gluon plasma. This wasn't a soup of water, but rather a seething, turbulent mixture of elementary particles, quarks and gluons, held together by the immense energy of the early universe. These particles, the most fundamental constituents of matter, weren't yet bound into protons and neutrons, the building blocks of atomic nuclei. They were constantly colliding and annihilating each other in a never-ending cascade of interactions. The temperature was so extreme, estimates range from 1 trillion to 10 trillion degrees Celsius, that the familiar rules of physics as we understand them simply didn't apply. The concepts of space and time, as we perceive them, were likely warped and distorted by the incredible energy densities. The quark-gluon plasma existed for a tiny fraction of a second, perhaps 10-12 seconds after the Big Bang. During this time, the universe was expanding incredibly rapidly, not just outwards, but also in a way that's difficult to comprehend. This rapid expansion is explained by the inflationary model, a cornerstone of the Big Bang theory. Inflation wasn't just about the universe getting bigger. It was a period of exponential growth, where the universe expanded by a factor of at least 10^26, a truly staggering number. It's like blowing up a balloon, but instead of expanding outwards, the balloon itself rapidly expands in all directions. The inflationary model arose from attempts to solve several puzzles surrounding the Big Bang. One was the horizon problem. The universe is remarkably uniform in temperature across vast distances, yet regions of the universe that are now widely separated would never have been in causal contact, meaning light couldn't have traveled between them during the time available since the Big Bang. Inflation provided a solution. It proposed that these regions were once much closer together and in thermal equilibrium before being rapidly stretched apart by the inflationary expansion. This explains the uniformity we observe today. Another puzzle was the flatness problem. The universe appears to be geometrically flat, which requires a very specific initial density. Inflation naturally explains this by stretching any initial curvature to near zero. The inflationary period wasn't a simple, gradual expansion. It's believed to have been driven by a hypothetical energy field called the inflaton. The inflaton possessed a large potential energy, and as it slowly rolled down this potential, it generated the exponential expansion. As the inflaton rolled, it also produced a quantum mechanical ripple, a tiny, random fluctuation in the energy density of the universe. These fluctuations are hugely important because they seeded the structures we see today: galaxies, stars, and planets. Think of it like dropping a pebble into a still pond. the ripples spread outwards, creating a complex pattern. These quantum fluctuations, amplified by the rapid expansion of the inflationary epoch, became the initial density variations that would eventually grow under the influence of gravity. Denser regions attracted more matter, leading to the formation of larger structures. It's crucial to understand that inflation didn't create these structures. It simply provided the initial conditions, the seeds, for their formation. The process of structure formation then relied on the well-known laws of gravity, as described by Einstein's theory of general relativity. As the universe continued to expand and cool after inflation, the energy of the inflaton gradually decayed, releasing its energy and reheating the universe. This reheating marked the transition from the inflationary epoch to the standard Big Bang expansion. The quarks and gluons, which had been confined within the inflaton field, were now free to combine and form protons and neutrons. These particles, in turn, fused together to create the first atomic nuclei, primarily hydrogen and helium, in a process called Big Bang nucleosynthesis. This process occurred around 3 minutes after the Big Bang, providing a precise prediction for the abundance of these elements, which has been confirmed by observations. The primordial soup, therefore, wasn't a passive collection of particles. It was a dynamic, energetic environment where the very laws of physics were being tested and where the fundamental ingredients of the universe were being forged. It's a reminder that our universe began from something extraordinarily complex and mysterious, and that the story of its formation is still being written as scientists continue to probe the earliest moments of time. The study of this era continues through sophisticated experiments like the Large Hadron Collider, which attempts to recreate the conditions of the primordial soup to study the properties of quarks and gluons directly. The echoes of this period, the subtle patterns in the cosmic microwave background radiation, the afterglow of the Big Bang, provide invaluable clues to unlocking the secrets of our universe's beginnings. The universe, after its explosive birth, wasn't immediately a smooth, homogeneous place. It was incredibly hot, a searing inferno filled with a dense, chaotic soup of particles, quarks and gluons swirling together in a state we call the quark-gluon plasma. This plasma, born from the initial expansion, cooled slowly over a period of time, eventually allowing these fundamental particles to combine and form protons and neutrons. But this early universe wasn't ready to form atoms. It was still dominated by this hot, ionized gas. Then, something extraordinary happened, a process that set the stage for the emergence of the cosmic microwave background radiation, the most compelling piece of evidence we have for the Big Bang theory. The universe continued to expand and cool, and as it did, the density of photons, those tiny packets of energy that make up light, began to decrease. However, this expansion wasn't uniform. Tiny fluctuations existed in the density of the early universe, slight variations here and there in the concentration of matter. These weren't random jitters. They were seeds sown by quantum mechanics that would eventually grow into the large-scale structures we observe today: galaxies, clusters of galaxies, and the vast cosmic web. These density fluctuations acted like gravitational lenses, amplifying certain regions and damping others. Now imagine this early universe as a vast, almost perfectly uniform bath of radiation. As the universe continued to expand, the wavelength of these photons stretched along with it. This is a phenomenon known as cosmological redshift. Just like a siren's sound changes pitch as it moves away from you, the wavelength of light stretches as the universe expands. Red light, which has the longest wavelength, stretches the furthest. This stretching is key to understanding the cosmic microwave background. The universe continued to expand and cool, reaching a point where it was cool enough for electrons and protons to combine and form neutral hydrogen atoms, a transition known as recombination. Before recombination, the universe was opaque, a dense fog of charged particles constantly scattering the photons. But after recombination, suddenly, there were no more free electrons to scatter the photons. The photons were finally free to travel unimpeded across the universe. These photons, released during recombination, have been traveling through space ever since, albeit with their wavelengths stretched to an enormous extent. They've been riding the expansion of the universe, and as they've traveled for approximately 13.8 billion years, their energy has decreased dramatically, and their wavelengths have expanded even further. This stretching has shifted them from visible light into the microwave portion of the electromagnetic spectrum, hence the name, cosmic microwave background radiation. The CMB isn't a single, uniform glow. It's actually incredibly detailed, exhibiting tiny temperature fluctuations, or anisotropies, across the sky. These anisotropies are the remnants of those initial density fluctuations, the seeds of structure that existed in the very early universe. Some regions of the CMB are slightly hotter than average, while others are slightly cooler. These temperature differences are incredibly small, on the order of a few parts per million, but their precise measurements provide a wealth of information about the early universe. Scientists use highly sensitive instruments, like the Planck satellite and the Wilkinson Microwave Anisotropy Probe, WMAP, to map the CMB with unprecedented accuracy. These instruments detect the faint microwave radiation coming from all directions in the sky. By analyzing the pattern of these temperature fluctuations, researchers can determine several fundamental properties of the universe. One of the most important things the CMB tells us is the geometry of the universe. The size and distribution of these temperature fluctuations depend on whether the universe is flat, curved like a sphere, or curved like a saddle. The CMB data strongly suggests that the universe is remarkably flat, a concept that has profound implications for our understanding of cosmology. Furthermore, the CMB allows us to precisely measure the age of the universe, which is estimated to be 13.8 billion years old. It also provides incredibly precise values for the density of matter and energy in the universe, including the amount of ordinary matter, dark matter, and dark energy. The proportions of these components are crucial to understanding the fate of the universe. The CMB is not just a relic of the Big Bang. It's a snapshot of the universe at a time just 380,000 years after the Big Bang, a period known as the recombination epoch. At this time, the universe had become transparent, and the CMB represents the earliest light that we can directly observe. It's a time capsule, preserving information about the conditions that existed at the very beginning. The analysis of the CMB is one of the most successful and well-supported pieces of evidence for the Big Bang theory. It's a testament to the power of observation and theoretical physics. It continues to be a primary focus of cosmological research, and ongoing observations are refining our understanding of the universe's origin, evolution, and ultimate destiny. It's a quiet, constant background glow, but within it lies a story of the universe's birth and a deep connection to our own existence. The universe, still incredibly young, wasn't filled with the familiar twinkling stars we see tonight. Instead, it was a profoundly dark and dense place, a cosmic fog almost entirely devoid of light. The remnants of the Big Bang, the energy released during that initial expansion, hadn't yet completely dispersed. This leftover energy, far hotter than anything we experience today, was the raw material for something extraordinary, the birth of the very first stars, what we call population III stars. These weren't like our sun, or any star that followed. They were colossal, born under vastly different conditions, and their existence is largely based on theoretical models and extrapolations from our understanding of physics. The universe at this time was almost entirely hydrogen and helium, but not in the same proportions as we see today. The Big Bang had created a much higher percentage of helium initially. There were virtually no heavier elements, no carbon, oxygen, or iron. This extreme lack of heavier elements is key to understanding how these first stars formed. Without them, the processes that govern star formation were radically different. The process began with incredibly dense regions of this early universe. These weren't clouds of gas like those forming stars today. These were essentially gravitational singularities, regions where gravity exerted an overwhelming force. These regions were so dense that the temperature was staggering, hundreds of millions of degrees Kelvin. At these temperatures, atoms themselves didn't exist in their normal state. Instead, the hydrogen and helium existed as a hot, ionized plasma, a swirling soup of charged particles. The immense gravity within these singularities caused these dense regions to collapse inwards. As they collapsed, the temperature and density increased dramatically. Unlike stars today which begin to fuse hydrogen in their cores, these first stars didn't have a core. Because there were no heavier elements to act as catalysts, the fusion process was entirely different. It wasn't the proton-proton chain, the standard mechanism for hydrogen fusion, that powered these stars. Instead, the collapse generated an intense burst of energy, triggering rapid and uncontrolled nuclear reactions. These reactions fused hydrogen directly into helium, but with a far greater efficiency than occurs in stars like our Sun. The energy released from these reactions wasn't contained. It blasted outwards, halting the further collapse of the star. This resulted in stars that were hundreds, perhaps even thousands, of times more massive than our Sun, truly behemoths of the early universe. Some models suggest sizes reaching 100,000 times the mass of the Sun. These population III stars weren't stable for long. Their enormous gravity pulled in surrounding gas, further fueling their fusion reactions. The intense radiation they emitted, primarily ultraviolet light, interacted with the surrounding hydrogen and helium, pushing it inwards and accelerating the fusion process. This created a runaway effect, driving the star to burn through its fuel at an astonishing rate. The sheer scale of these stars meant that their eventual demise was equally spectacular. When they finally exhausted their fuel, they didn't gently fade away like a white dwarf. Instead, they underwent a catastrophic core collapse supernova, far more powerful than any supernova we've observed since. These weren't the slow, graceful explosions that marked the end of many stars. They were incredibly violent events, ripping apart the star completely. The material ejected from these supernovae, the heavy elements forged within the star's core, was scattered across the surrounding space. This ejected material, enriched with elements like oxygen, carbon, and iron, became the raw material for the next generation of stars, population II and population I stars. It's important to understand that these early supernovae were crucial. They were the first factories for creating heavier elements, seeding the universe with the building blocks for planets and, eventually, life. These population III stars are incredibly difficult to observe directly. Their light was redshifted, stretched to longer wavelengths, due to the expansion of the universe. Furthermore, the intense ultraviolet radiation they emitted would have obscured any subsequent observations. Current research relies on computer simulations and theoretical models to try and reconstruct the properties of these elusive giants. Scientists are also searching for potential fossil evidence, faint echoes of their light in the spectra of distant galaxies. The study of population III stars isn't just about understanding the birth of the first stars. It's about understanding the very origins of the elements that make up our world, ourselves, and everything around us. It's a window into a time when the universe was fundamentally different, a period of immense change and creation, driven by the fiery power of these extraordinary, colossal stars. It's a story written in the light itself, a faint, ancient whisper from the dawn of time. The universe, still a relatively cool and diffuse place after the Big Bang, wasn't immediately filled with the familiar elements we see around us: oxygen, nitrogen, iron. Instead, it was primarily composed of hydrogen and helium, the direct products of the initial expansion and the energy released in that first, explosive moment. These elements, abundant but not diverse enough to form planets or sustain life as we know it. The seed of change, the engine of diversity, lay within the very stars themselves. These celestial furnaces, born from slight density fluctuations in the early universe, began to draw in vast quantities of hydrogen, fusing it together in a process called stellar nucleosynthesis. This wasn't a simple, one-step reaction. It was a complex series of nuclear reactions, driven by immense gravitational pressures and temperatures within the star's core. The fundamental process began with the proton-proton chain, dominant in stars like our Sun. Here, 4 protons, hydrogen nuclei, collide with sufficient energy to fuse and create a helium nucleus, releasing energy in the form of gamma rays and neutrinos. A positron, a positively charged electron, is also produced. This process happens repeatedly, converting hydrogen into helium. However, larger, more massive stars had a different story to tell. They possessed enough gravitational force to build up core temperatures and pressures far exceeding those found in smaller stars. This extreme environment allowed for a more advanced stage of fusion to commence, the CNO cycle. Carbon, nitrogen, and oxygen acted as catalysts, dramatically accelerating the rate at which hydrogen was converted into helium. These elements, initially created through earlier processes, became crucial players in this larger, more efficient fusion pathway. As a star steadily burned through its hydrogen fuel, the core began to contract and heat up further. Eventually, the core became dense enough to fuse helium into carbon. This wasn't a straightforward conversion either. It required a significant amount of energy and a sustained period of intense pressure. Carbon then began to fuse with other carbon nuclei, building up heavier elements like oxygen and neon. These stages, known as the advanced burning stages, represent the core of a star's life, transforming the elements created earlier into increasingly heavier ones. But the story doesn't end with carbon and oxygen. In even more massive stars, the core could reach temperatures hot enough for neon to fuse into magnesium and oxygen, and eventually, oxygen into silicon and nickel. These stages represent the most extreme forms of nucleosynthesis, demanding incredible conditions and energy. As the star consumes its fuel, it develops an onion-like structure, with layers of progressively heavier elements being created within its core, and then transported outwards through a process called convection. The ultimate fate of these massive stars is spectacular, a supernova. When the star's core collapses under its own gravity, it triggers a colossal explosion, scattering the newly synthesized elements across vast distances of space. This supernova remnant is a breathtaking display of energy and a crucial mechanism for distributing elements heavier than iron. The intense heat and pressure of the explosion allow for the creation of elements like gold, platinum, and uranium, elements not found in significant quantities within the star itself. Now, consider that the elements produced within stars aren't just trapped within those stars. As they die, either through a gentle planetary nebula or a violent supernova, they're ejected into the surrounding interstellar medium. This enriched material then becomes incorporated into new generations of stars and planetary systems. The planets we inhabit, and ultimately life itself, are made of stardust, elements forged in the hearts of long-dead stars. The distribution of these heavier elements isn't uniform. Supernova explosions are particularly effective at dispersing elements over large distances, leading to regions of higher elemental abundance. Conversely, areas shielded from the direct effects of a supernova may retain a lower concentration of heavier elements. This creates variations in the composition of galaxies, influencing the formation of new stars and planetary systems. Furthermore, the process of stellar nucleosynthesis isn't a single, static event. It's a continuous cycle, driven by the birth, life, and death of stars. Each generation of stars inherits the elements from its predecessors, adding to the cosmic inventory and enriching the universe with the building blocks of planets and life. This understanding fundamentally changes our perspective on the universe, demonstrating that we are, quite literally, made of star stuff, a direct legacy of the universe's most powerful processes. It's a humbling realization, isn't it? To think that the elements composing our bodies, the Earth, and everything around us originated in the cores of distant, exploded stars. The universe, in its grand and elegant way, is constantly recycling itself, transforming matter and creating the conditions for new forms of existence to emerge. This ongoing process of stellar nucleosynthesis is a testament to the dynamism and interconnectedness of the cosmos. The universe, having spent billions of years building up complexity through stellar nucleosynthesis, still held a surprising capacity for dramatic change. Not all supernovae, those spectacular, violent deaths of massive stars, were created equal. Some were quiet, relatively gentle affairs, fading quickly after their brilliant displays. But then there were the type Ia supernovae, and these were something entirely different, a cosmic fireworks display of a scale almost unimaginable. Their origins lie in the final, desperate moments of a specific type of binary star system. These systems invariably contained a white dwarf, the dense, remnant core of a star that has exhausted its nuclear fuel. A white dwarf isn't technically a star anymore. It no longer generates energy through fusion. However, it remains incredibly hot and dense, possessing a strong gravitational pull. Orbiting this white dwarf is another star, often a red giant, which periodically sheds material, primarily hydrogen and helium, onto the white dwarf's surface. This isn't a casual, slow process. As the material accumulates, the white dwarf's mass increases, relentlessly crushing its core. The white dwarf has a theoretical mass limit, known as the Chandrasekhar limit, about 1.4 times the mass of our Sun. This limit is crucial. When the white dwarf approaches this boundary, the internal pressure, which was previously resisting the relentless inward pull of gravity, can no longer hold. Suddenly, runaway nuclear fusion begins in the core, primarily carbon fusion. This isn't the controlled, sustained fusion that powers a main sequence star. This is an incredibly rapid, uncontrolled reaction. Carbon atoms begin to fuse at an unprecedented rate, converting into heavier elements: oxygen, neon, magnesium, and eventually silicon. The energy released during this fusion is enormous, far exceeding anything produced during the star's lifetime. This isn't a gradual increase in brightness. It's an instantaneous cataclysmic burst. The entire white dwarf detonates in a brilliant flash of light, a type Ia supernova. The explosion ejects the entire star into space, often at speeds reaching a significant fraction of the speed of light. This explosion is so powerful that it can briefly outshine an entire galaxy. The light spectrum produced by a type Ia supernova is remarkably consistent, meaning that they all look essentially the same, regardless of their distance. This consistency is what makes type Ia supernovae so vital to our understanding of the universe's large-scale structure. They've become known as standard candles. Consider a dimmer switch. You know that a specific setting represents a certain level of brightness. If you observe two objects that appear to be the same brightness, you can deduce that the dimmer object is actually farther away. Similarly, if we observe a type Ia supernova and measure its apparent brightness, how bright it appears to us on Earth, we can compare that brightness to its redshift, which is a measure of how much its light has been stretched due to the expansion of the universe. The relationship between a supernova's apparent brightness and its redshift allows astronomers to calculate its distance. Because type Ia supernovae are standard candles, we can use them to determine distances to faraway galaxies. The further away a type Ia supernova is, the greater its redshift will be, and the fainter it will appear. This method, known as standard candle cosmology, has been instrumental in determining the accelerating expansion of the universe. Furthermore, the energy released by a type Ia supernova plays a significant role in regulating star formation. When a supernova explodes, it scatters heavy elements heavier than helium, into the surrounding interstellar medium. These elements, created in the core of the exploding white dwarf, are the building blocks for new stars and planetary systems. Without supernovae, the universe would be dominated by hydrogen and helium, and the formation of more complex elements and the subsequent creation of planets, like the one we call home, would have been fundamentally impossible. The sheer number of Type Ia supernovae occurring throughout the universe, estimates suggest dozens per century in our observable universe, contributes significantly to the overall energy budget. They represent a substantial source of radiation, influencing the thermal properties of the intergalactic medium and interacting with the distribution of galaxies. The study of these explosions provides invaluable clues about the dynamics of galaxy clusters, the formation of large-scale structures, and the ongoing evolution of the cosmos. The remnants of these explosions, the expanding supernova remnants, continue to radiate energy for thousands of years, further contributing to the universe's complex interplay of energy and matter. It's a final, spectacular burst of creation and destruction, a fundamental process in the universe's ongoing story. Understanding Type Ia supernovae is not just about studying a single event. It's about understanding the mechanisms that drive the universe's growth and change. The universe, having birthed its first generations of stars, colossal entities forged from the very fabric of space and time, continued its grand, dynamic evolution. While these early stars ultimately met their fiery ends in spectacular supernova explosions, their deaths weren't always the complete story of stellar evolution. Sometimes, the remnants of these collapses held an extraordinary secret, the beginnings of black holes. Initially, these weren't the colossal gravitational giants we often picture, but rather smaller, stellar-mass black holes, born from the cores of massive stars that had exhausted their nuclear fuel. When a particularly large star, far exceeding the mass of our Sun, reaches the end of its life, the process of nuclear fusion within its core ceases. For eons, the outward pressure generated by fusion battling the inward pull of gravity had kept the star stable. Without this outward pressure, gravity relentlessly triumphs. The core begins to contract violently, accelerating inward with unimaginable force. As the core shrinks, it heats up dramatically. This extreme heat eventually triggers a catastrophic collapse. The process isn't a sudden implosion, but rather a complex sequence of events. Layers of the star's outer material, stripped away by the preceding fusion stages, spiral inward towards the now compressed core. This inward rush of material forms what's called a supernova remnant, a swirling cloud of gas and debris. At the very center of this collapse, the core continues to shrink until it becomes a singularity, a point of infinite density, where all the star's mass is concentrated. This singularity is the birthplace of a stellar mass black hole. The immense gravitational pull of this newly formed black hole dictates the fate of the surrounding material. The supernova remnant, instead of dispersing into space, is drawn in and consumed by the black hole. This process, known as accretion, dramatically increases the black hole's mass. Material doesn't simply disappear, it's converted into energy, a consequence of Einstein's famous equation, E equals mc2, where energy E is equivalent to mass m multiplied by the speed of light c squared. The accretion disk, a swirling vortex of gas and dust heated to incredible temperatures by friction, emits intense radiation across the electromagnetic spectrum, from radio waves to X-rays, making these black holes detectable across the cosmos. However, the story doesn't end with stellar mass black holes. Over vast timescales, these smaller black holes themselves could grow, albeit slowly. They could accrete matter from their surroundings, drawing in gas and dust from nearby clouds. They could even, in rare instances, merge with other black holes, a process governed by the same principles of gravity. These mergers release tremendous amounts of energy in the form of gravitational waves, ripples in spacetime itself, predicted by Einstein and directly detected by sophisticated instruments on Earth. Then there's the truly remarkable evolution of the universe's largest black holes, the supermassive black holes that reside at the centers of most, if not all, galaxies. The precise mechanisms for their formation are still being actively researched, and it's believed that multiple processes could have been at play. One leading theory suggests that they formed from the collapse of massive gas clouds in the early universe, perhaps facilitated by the gravitational influence of smaller black holes. Another proposes that they grew steadily over billions of years by accreting vast quantities of gas and dust, fueled by the intense star formation activity within their host galaxies. Furthermore, the mergers of stellar mass black holes, operating over immense stretches of time, undoubtedly contributed to the growth of these behemoths. The seeds of these supermassive black holes, therefore, are rooted in the evolution of smaller black holes, constantly feeding and growing. The growth rate of these black holes isn't constant. They can experience periods of rapid accretion followed by periods of relative quiescence, depending on the availability of surrounding material. The existence of supermassive black holes profoundly impacts their galaxies. Their gravity influences the motions of stars and gas within the galaxy, shaping the overall structure and dynamics. They also play a role in regulating star formation. Powerful jets of material, launched from the poles of the black hole due to complex magnetic field interactions, can heat surrounding gas, suppressing star formation in certain regions while triggering it in others. It's important to remember that black holes aren't simply cosmic vacuum cleaners, relentlessly consuming everything in their path. While they do accrete matter, they also exert a gravitational influence that attracts and holds galaxies together. The immense gravitational forces generated by supermassive black holes are essential for the stability of galaxies, preventing them from flying apart. These black holes are therefore integral components of the universe's grand architecture. The study of black holes continues to be a frontier of modern astrophysics, offering invaluable insights into gravity, space-time, and the evolution of the universe. As technology advances, we are increasingly able to observe and characterize these enigmatic objects, bringing us closer to understanding their role in the cosmic narrative. The journey from the collapse of massive stars to the formation of supermassive black holes represents a fundamental chapter in the ongoing story of the universe, a story of immense forces, spectacular events, and ultimately, the creation of some of the most powerful and mysterious objects in existence. The universe, after the initial burst of creation and the formation of the first stars and heavier elements, wasn't immediately a collection of neatly arranged galaxies. Instead, it began a process of intricate building, a cosmic game of cosmic Lego, where smaller clumps gradually assembled into larger, more complex structures. This ongoing process, now understood through a compelling model, describes how galaxies like our own Milky Way came to be and how they continue to evolve. At its core, the hierarchical model suggests that galaxies didn't simply appear fully formed. They grew through a series of mergers and additions, all orchestrated by the invisible hand of gravity and the pervasive influence of dark matter. The seeds of galaxy formation were sown in the early universe, not as distinct galaxies, but as subtle overdensities in the primordial soup of dark matter. Dark matter, as we've explored, doesn't interact with light, meaning we can't directly see it. However, its gravitational pull exerted a tremendous influence, drawing in surrounding matter, primarily hydrogen and helium gas, into these initial concentrations. These overdense regions acted like gravitational wells, attracting more and more material. As these clumps grew, their own gravity intensified, accelerating the process of accretion, the gradual accumulation of material from the surrounding space. These early structures, often referred to as proto-galaxies, weren't stable. They were constantly jostled and disrupted by the turbulence of the early universe. They collided with each other, and these collisions were far more than just bumping into each other. They were gravitational dances of immense power. When two proto-galaxies collided, their gravitational forces combined, creating an even larger, denser object. these mergers weren't gentle embraces. They were chaotic events characterized by intense compression of gas, heating, and the formation of spectacular structures known as starburst galaxies. During these starbursts, vast numbers of new, massive stars were born, fueled by the newly available gas. The resulting supernovae, though a violent consequence of stellar deaths, played a critical role in enriching the surrounding space with heavier elements, further feeding the next generation of star formation. The scale of these mergers wasn't limited to small proto-galaxies. The hierarchical model predicts that these early galaxies themselves then merged with progressively larger structures. Think of it like a snowball rolling down a hill. It picks up more snow and grows larger and larger. Galaxies don't just sit still. They actively participate in a cosmic dance of mergers, creating structures that are vastly more complex than the original building blocks. These mergers led to the formation of elliptical galaxies, large, smooth, and often reddish in color, which typically form through the repeated merging of spiral galaxies. But the story doesn't end with just the merging of galaxies. A crucial, underlying component of this process is the role of dark matter halos. These halos, which are far more abundant than the visible matter within galaxies, provided the gravitational scaffolding for all of this to happen. They are enormous, diffuse regions of dark matter that surround and permeate galaxies. The mass of a dark matter halo dictates the scale and shape of the galaxy that forms within it. The halo's gravity is the primary driver of galaxy formation, pulling in and holding together the visible matter, gas, dust, and stars that resides within the galaxy. The size of a dark matter halo determines the size of the galaxy that can form within it. Larger halos can accommodate larger galaxies, and smaller halos can only support smaller, less massive galaxies. As galaxies merge and accrete, their dark matter halos also merge, creating even larger and more complex halos. This process explains why galaxies are rarely found alone. They are almost always embedded within vast, extended halos of dark matter. Furthermore, the distribution of dark matter within these halos isn't perfectly smooth. Simulations show that dark matter halos often have a cuspy distribution, meaning they are denser towards the center and more diffuse further out. This influence affects the shape and rotation of the galaxy residing within the halo. The way stars orbit within a galaxy is, in part, determined by the shape of its dark matter halo. This ongoing interplay between visible matter and dark matter is what creates the diverse range of galaxy shapes, from the spiral arms of our Milky Way to the elliptical forms observed in other galaxies. It's a continuous feedback loop. Mergers trigger starbursts, which produce supernovae that seed the galaxy with heavier elements. These heavier elements then become incorporated into new stars, which eventually die and contribute to the next generation of supernovae. And this cycle continues, shaping the evolution of galaxies over billions of years. It's a remarkably elegant and powerful model, one that accurately explains the vast majority of the galaxies we observe in the universe today. The story of galaxy formation is, quite simply, the story of how the universe built itself, one gravitational dance at a time. The universe, even at its most distant, doesn't always whisper in gentle tones. Sometimes it erupts in a roar, a blinding flash of energy that dramatically reshapes the galaxies around it. These aren't ordinary events. They're the signatures of active galactic nuclei, or AGN. For eons, we've understood galaxies as collections of stars, gas, and dust, generally peaceful and predictable. But within some galaxies, particularly at their centers, a completely different story unfolds, a story of immense power and extreme conditions. The engine driving these AGN is primarily a supermassive black hole, a gravitational behemoth millions or even billions of times the mass of our sun. These black holes aren't simply sitting quietly, absorbing matter. Instead, they're actively feeding, growing larger with each meal. This feeding process is what creates the phenomenal energy output we observe. At the heart of this process is an accretion disk. Imagine a swirling vortex of gas and dust pulled relentlessly towards the black hole. As material spirals inward, it doesn't simply fall straight in. Instead, due to its angular momentum, its tendency to keep spinning, it forms a flattened disk. This disk isn't static. It's a turbulent, chaotic region where friction and gravitational forces heat the gas to incredible temperatures, hotter than the core of our sun. This extreme heat causes the gas to emit tremendous amounts of radiation across the electromagnetic spectrum, from radio waves to X-rays and ultraviolet light. This is the dominant way we detect AGN, as the radiation is often incredibly bright and permeates vast distances. The accretion disk isn't just a source of radiation. It's also responsible for launching spectacular jets of particles outwards, perpendicular to the disk. Exactly how these jets are formed is still an area of active research, but the prevailing theory involves magnetic fields. As the material in the accretion disk rotates, it generates powerful magnetic fields. These magnetic fields become twisted and tangled, and the black hole's intense gravity can channel this energy into two powerful jets that shoot out from the poles of the black hole, traveling at near-light speeds. These jets can extend for enormous distances, far beyond the host galaxy itself, often forming complex, tangled structures. The structure of these jets isn't always simple. They can be threaded with ridges and loops, creating stunning visual displays observed in radio telescopes. These structures, known as hot spots, are believed to be created by the interaction of the jet with the surrounding magnetic fields and the interstellar medium. These jets fundamentally alter the environment around the AGN. They heat the gas in the host galaxy, suppressing star formation in the immediate vicinity. The powerful radiation also strips away gas and dust, effectively cleaning out the galactic center. These powerful AGN aren't just fascinating objects in their own right. They profoundly influence their host galaxies. The intense radiation and jets disrupt the normal processes of star formation, dramatically changing the galaxy's evolution. Moreover, the energy deposited by the AGN can drive outflows of gas and dust from the galaxy's disk, creating large, expanding bubbles of hot, ionized gas, a phenomenon sometimes referred to as a blown bubble. These bubbles can reshape the entire galaxy, carving out cavities and influencing the distribution of gas and dust. Within this dramatically altered environment, galaxies hosting AGN are classified as quasars. The term quasar comes from quasi-stellar radio source, reflecting their initially mysterious nature as objects that appeared similar to stars, but emitted enormous amounts of radio waves. Now, we understand that quasars are, in essence, the most extreme form of AGN. They are characterized by their incredibly high luminosities. They are among the brightest objects in the universe, and their characteristic broad emission lines in their spectra, which are produced by the rapid motion of gas within the accretion disk. It's important to note that not all AGN are equally powerful. Some are low-level AGN, characterized by weaker emission lines and lower overall luminosities. These can be found in many galaxies, including our own Milky Way. The presence of a low-level AGN in the Milky Way, known as Sagittarius A, is a remarkable demonstration of the ubiquity of these powerful objects. This AGN is powered by a supermassive black hole at the center of the galaxy, gradually accreting gas and dust over billions of years. The study of AGN and quasars provides invaluable insights into the processes governing galaxy evolution. By observing these energetic objects, scientists can learn about the growth of supermassive black holes, the mechanisms of accretion, and the interplay between black holes and their host galaxies. Furthermore, the radiation emitted by quasars allows us to probe the distant universe, providing a glimpse into the conditions that existed when the universe was much younger. As we continue to observe these powerful cosmic engines, we refine our understanding of the universe's complex history. The roars of AGN, though distant, tell a compelling story of gravity, accretion, and the relentless evolution of galaxies, a story that continues to unfold with each new discovery. And as we continue to push the boundaries of astronomical observation, perhaps one day we'll fully unravel the secrets hidden within these extraordinary objects. The universe, as we've come to understand it, isn't quite as full of the stuff we can see, stars, planets, and gas, as our initial observations might suggest. There's a hidden presence, a ghostly influence that subtly shapes the cosmos. This is dark matter, and for decades, scientists have been engaged in a fascinating and frustratingly complex hunt to understand its nature. The story begins with observations that simply couldn't be explained by the visible matter alone. Galaxies rotate much faster than they should, given the amount of stars and gas they contain. Stars at the outer edges of spiral galaxies are whirling around the galactic center at speeds that would fling them outwards, ripping the galaxy apart. It's as if an unseen force is holding everything together, providing the extra gravitational glue. This discrepancy wasn't a minor detail, it was a fundamental problem. Physicists began to suspect that there was a significant amount of mass present that wasn't directly observable. These early calculations, based on the rotation curves of galaxies, became the cornerstone of the dark matter hypothesis. It wasn't enough to simply say, "We don't know what's there." The evidence pointed to a substantial, undetected mass component. The search for this dark matter has taken two primary approaches: direct detection and indirect detection. Direct detection attempts to actually catch dark matter particles interacting with ordinary matter. Massive detectors, often buried deep underground to shield them from cosmic rays and other background noise, are designed to observe the faint signals that would occur if dark matter particles collide with atomic nuclei. These detectors typically use extremely sensitive materials like liquid xenon or germanium, looking for flashes of light or ionization caused by a dark matter particle striking. These experiments are incredibly challenging because dark matter particles, if they exist, are thought to interact with ordinary matter very weakly, if at all. The sensitivity of these detectors is constantly being pushed to new limits, but so far, no definitive detection has been made. There have been tantalizing hints, brief, unexplained energy signals, but none that have held up under rigorous scrutiny. The lack of a clear signal doesn't necessarily mean dark matter doesn't exist. It simply means the interaction is far more subtle than initially anticipated. Meanwhile, scientists are pursuing indirect detection methods. These focus on observing the products of dark matter annihilation or decay. If dark matter particles collide and annihilate each other, they could produce detectable particles like gamma rays, positrons, or antiprotons. The Large Hadron Collider at CERN, designed to smash protons together at nearly the speed of light, is also playing a role in this search. Scientists are looking for evidence of dark matter annihilation products produced in these high-energy collisions. Another area of investigation involves observing the cosmic microwave background radiation, the afterglow of the Big Bang. Small fluctuations in the CMB can provide clues about the density of dark matter in the early universe. The shape of these fluctuations is intimately linked to the amount and distribution of dark matter, offering a way to constrain its properties. Beyond simply detecting dark matter, scientists are also trying to understand what it is. Numerous theoretical candidates have been proposed, each with its own set of characteristics and potential implications. One of the most popular candidates is weakly interacting massive particles, or WIMPs. These hypothetical particles are thought to have a mass between 10 and 1,000 times that of a proton and interact with ordinary matter through the weak nuclear force, the same force responsible for radioactive decay. WIMPs gained prominence because they naturally arise in some extensions of the standard model of particle physics. Another compelling candidate is axions. Axions are extremely light, hypothetical particles originally proposed to solve a different problem in particle physics, the strong CP problem. They are extremely weakly interacting and much lighter than WIMPs, potentially explaining the lack of observed dark matter signals. The properties of axions are finely tuned to match the observed rotation curves of galaxies, making them a particularly attractive candidate. Recent research has suggested that axions could even be produced in significant numbers within the Milky Way itself. Furthermore, scientists are exploring alternative theories beyond simply adding new particles. Modified Newtonian dynamics, MOND, proposes that gravity behaves differently on very large scales, eliminating the need for dark matter altogether. However, MOND struggles to explain observations at the scale of galaxy clusters. The distribution of dark matter isn't uniform. It forms vast halos that surround galaxies and galaxy clusters. These halos play a crucial role in shaping galaxy structures. They provide the gravitational scaffolding upon which galaxies form and evolve. The observed rotation curves of galaxies, the gravitational lensing of light by massive objects, and the formation of large-scale cosmic structures all point to the existence of these dark matter halos. Understanding the precise shape and density distribution of these halos is a key piece of the puzzle. The quest to understand dark matter remains one of the most significant challenges in modern astrophysics and particle physics. While we haven't yet directly detected dark matter, the ongoing experiments, theoretical developments, and observational data are slowly but surely refining our understanding of this elusive substance. It's a story of detective work, a painstaking search for the invisible threads that hold the universe together, and a reminder that some of the greatest mysteries lie hidden just beyond our current ability to see. The universe, as we've come to understand it, isn't simply expanding. It's expanding at an accelerating rate. This discovery, made in the late 1990s, was a genuine surprise, a cosmic revelation that shifted our entire understanding of the cosmos. Initially, cosmologists had predicted that the expansion, begun with the Big Bang, would gradually slow down due to the gravitational pull of all the matter within the universe. After all, gravity is an attractive force, and it should be working against the outward momentum of the expansion. However, observations of distant Type Ia supernovae, incredibly bright, standard candles in the night sky, revealed something startling. These supernovae were fainter than expected, indicating they were further away than predicted. This meant the universe's expansion wasn't slowing, it was speeding up. The most direct explanation for this accelerating expansion is something called dark energy. We don't know what it is exactly, but we know it's exerting a repulsive force, a kind of anti-gravity that's pushing space itself apart. It's as if the universe has discovered a new force, one that opposes gravity on the largest scales. The amount of dark energy constitutes approximately 68% of the universe's total energy density, dwarfing the contributions of dark matter and ordinary matter, the stuff we're made of, the stars and galaxies. It's a humbling reminder of how much we still don't know. The cosmological constant, often denoted by the Greek letter lambda, was initially proposed as a simple explanation for dark energy. It's a constant energy density that permeates all of space, and it's inherent to Einstein's theory of general relativity. Einstein introduced the cosmological constant into his equations to create a static universe, one that wasn't expanding or contracting. However, when Hubble discovered the universe's expansion, Einstein famously called the cosmological constant his biggest blunder. But the cosmological constant isn't entirely dismissed. It still represents the simplest explanation. The problem lies in the enormous discrepancy between the theoretical value predicted by general relativity and the observed value of dark energy. The theory predicts a value roughly 120 orders of magnitude larger than what we actually observe. This is a problem so vast it's almost incomprehensible, a fundamental tension at the heart of modern cosmology. Given this huge discrepancy, physicists and astronomers have explored alternative models for dark energy. One popular idea is quintessence. Instead of a constant, quintessence proposes that dark energy is a dynamic, evolving field, similar to a scalar field that permeates the universe. Unlike the cosmological constant, quintessence's energy density could change over time, meaning its repulsive effect might also vary. Scientists are actively searching for evidence of this dynamic behavior, looking for subtle changes in the expansion rate of the universe. Another possibility is phantom energy. This even more radical model suggests that dark energy isn't just a constant or a dynamic field. It's an energy with an equation of state, a mathematical relationship between its pressure and density. That's even more extreme than quintessence. Phantom energy could cause the expansion of the universe to accelerate without bound, eventually leading to a big rip, where the universe tears itself apart as space itself expands faster than the speed of light. While currently considered unlikely, it's a fascinating, albeit unsettling, theoretical possibility. Furthermore, some researchers are exploring modifications to general relativity itself. Perhaps our understanding of gravity, at the largest scales, is incomplete. Modified Newtonian dynamics, MOND, attempts to explain galactic rotation curves, the speeds at which stars orbit their galaxies, without invoking dark matter. While MOND doesn't directly address dark energy, it suggests that general relativity might need refinement in the absence of large-scale structures. The pursuit of understanding dark energy is driving a significant amount of astronomical research. Astronomers are using powerful telescopes, like the James Webb Space Telescope, to observe distant galaxies and measure their expansion rates with ever-increasing precision. They're also studying the cosmic microwave background, the afterglow of the Big Bang, for subtle clues about the universe's initial conditions and the nature of dark energy. The ongoing quest to unravel the mystery of dark energy highlights the profound challenges and exciting opportunities within cosmology. It's a story of discovery, of confronting our assumptions, and of pushing the boundaries of human knowledge. It underscores that our understanding of the universe is constantly evolving, and that the most surprising discoveries often lie just beyond our current grasp. Ultimately, the nature of dark energy remains one of the biggest unsolved puzzles in science. It's a testament to the vastness and complexity of the cosmos, and a reminder that the universe still holds countless secrets waiting to be revealed. Perhaps future generations of scientists will finally unlock the secrets of this elusive force, forever changing our understanding of the universe and our place within it. The universe, just a few 100 million years after the Big Bang, wasn't the dark, mostly empty place we often picture. It was a complicated, swirling soup of gas, primarily hydrogen and helium, still incredibly hot. This wasn't a silent void. It was a place of constant, violent activity. The remnants of the Big Bang, the afterglow of creation, continued to radiate outwards as the cosmic microwave background, but this radiation wasn't the dominant factor. Something new was about to emerge, something intensely energetic, something that would fundamentally change the universe's appearance. The process began with the birth of the very first stars. These weren't the grand, stately giants we see today. These first stars, often referred to as population III stars, were colossal, many times more massive than our sun. They formed rapidly, fueled by the dense, pristine gas left over from the Big Bang. Because almost all the elements heavier than hydrogen and helium hadn't yet been created, they were truly primordial, built entirely of the simplest elements. Their formation was a chaotic event, occurring in regions of exceptionally high density, often within the cores of early galaxies. The intense gravity pulled in vast amounts of gas, triggering rapid nuclear fusion within their cores. These stars shone with a ferocity that the early universe had never witnessed. They emitted tremendous amounts of ultraviolet UV radiation, far more intense than anything we see from stars today. This UV light wasn't gentle. It was incredibly energetic, capable of ripping electrons away from atoms. As these massive stars lived their short, brilliant lives, they exploded in spectacular supernovae, scattering these newly forged elements, forged in their cores and then flung outwards across the surrounding space. This scattered material, infused with heavier elements, became the building blocks for subsequent generations of stars and galaxies. But the immediate impact of these early supernovae was far more dramatic. The intergalactic medium, the vast space between galaxies, was almost entirely neutral at this time. This means that the hydrogen atoms within it didn't have their electrons stripped away. They existed in a state of balance, with each atom having a perfect pair of electrons. However, the intense UV radiation from the first stars and supernovae was relentless. It began to systematically strip electrons from the hydrogen atoms in the intergalactic medium. Every photon of UV light it encountered had enough energy to dislodge an electron, leaving behind a positively charged ion, a hydrogen ion. This process created a plasma, a soup of free electrons and ions throughout the universe. The neutral hydrogen began to disappear, replaced by an ionized plasma. Crucially, the process wasn't simply about individual stars. The early universe was riddled with the remnants of these first supernovae, creating a vast, diffuse bubble of ionized gas. These supernovae, though short-lived, were incredibly efficient at injecting energy into the intergalactic medium. The energy didn't just heat the gas, it actively drove the ionization process. As more and more hydrogen was ionized, the intergalactic medium became increasingly transparent to this UV radiation. The radiation, now traveling unimpeded through the plasma, could propagate further and further across the universe. This propagation of UV light is what we now understand as the epoch of reionization. It was a complex, dynamic process, a cosmic game of tag, where UV photons were repeatedly scattered and absorbed, ultimately transforming the universe from a neutral, opaque state to an ionized, transparent one. Alongside the first stars, another significant contributor to reionization came from a related phenomenon: quasars. Quasars, as we've discussed, are supermassive black holes residing at the centers of distant galaxies. When a black hole accretes matter, gas, and dust spiraling inwards, it forms an accretion disk around itself. This disk becomes incredibly hot and bright, emitting enormous amounts of energy across the electromagnetic spectrum, including copious amounts of UV radiation. These quasars, located in the early universe, were some of the most luminous objects ever observed. Their immense energy output dramatically accelerated the ionization process, further contributing to the reshaping of the intergalactic medium. The combined effect of the first stars and the earliest quasars effectively turned on the universe, allowing light to travel freely across vast distances, paving the way for the formation of the first galaxies. The reionization epoch wasn't a single, instantaneous event. It was a gradual process, spanning perhaps hundreds of millions of years. As the intergalactic medium became increasingly ionized, the UV radiation from the early stars and quasars could travel further, and more of the universe became transparent. The process continued, driven by the ongoing birth and death of stars and the activity of supermassive black holes. It was a pivotal moment in the universe's history, a transition that fundamentally altered its structure and ultimately enabled the formation of the galaxies and large-scale structures we see today. The light that reaches us from those distant times carries the imprint of this transformation, a faint echo of the universe's rebirth. The vastness of space, a canvas painted with the echoes of the Big Bang, held within it the nascent remains of our own cosmic neighborhood. Following the energetic birth of the first stars and the subsequent epoch of reionization, a swirling cloud of gas and dust, remnants of supernovae and stellar winds, lingered in the Milky Way's spiral arms. This wasn't a uniform cloud. It possessed a subtle, underlying rotation, a gentle spin inherited from the gravitational interactions within the galaxy. Within this rotating cloud, A localized region began to draw in surrounding material, slowly concentrating itself. This concentration wasn't a sudden event, but rather a gradual intensification, driven by gravity's inexorable pull. As the cloud compressed, the atoms within began to vibrate with increased energy, transitioning from a state of relative calmness to a restless dance. This dance was crucial because the cloud wasn't composed of simple, uniform gases. It was, in essence, a cosmic stew of elements: hydrogen, helium, oxygen, iron, and a host of heavier elements forged in the hearts of dying stars. These elements, born through nuclear fusion and scattered across space by supernova explosions, were suspended within the cloud. The key to understanding the formation of our solar system lies in the concept of temperature variations within this rotating cloud. Not all parts of the cloud were equally cold. Regions closer to the galactic center, bathed in the light and heat of nearby stars, experienced higher temperatures. Further out, shielded from this intense radiation, the temperature plummeted. These temperature differences instigated a fundamental process known as condensation. Just as water vapor in the air condenses into droplets when cooled, various elements within the cloud began to condense out of a gaseous state and solidify. The colder regions, particularly those beyond a distance of roughly 30-50 astronomical units from the center of the cloud, became significantly colder than the warmer inner regions. This colder temperature dramatically lowered the energy available for the atoms to maintain their gaseous state. Hydrogen, being the most abundant element, began to condense first, forming microscopic grains of ice, not the kind you'd find in a freezer, but complex mixtures of water ice, ammonia ice, methane ice, and even ices containing heavier elements. These icy grains, though tiny, often only a few millimeters across, were incredibly important. They acted as seeds, providing the raw materials for planet formation. Alongside hydrogen ice, other elements like oxygen and carbon also began to condense, forming their own distinct ices. The presence of these ices was critical because they could trap volatile compounds, creating a vast reservoir of materials that wouldn't otherwise exist in solid form. Simultaneously, within the warmer inner regions of the protoplanetary disk, the rotating, flattened cloud, the temperatures were high enough to allow materials like metallic iron and nickel to remain solid. These heavier elements, concentrated in the inner parts of the disk, were subject to gravitational forces far stronger than those acting on the icy grains. This strong gravity caused these metallic clumps to clump together, eventually growing into larger and larger bodies. The exact process of how the sun formed is still being refined by scientists, but the prevailing theory suggests that a dense, swirling core of gas and dust coalesced within the inner disk. This core, perhaps a few times the mass of Jupiter, continued to accrete material from the surrounding disk. As it grew, its own gravity intensified, accelerating the rate of accretion. The immense pressure and heat generated within the core eventually triggered nuclear fusion, the process that converts hydrogen into helium, releasing tremendous amounts of energy. And that, quite spectacularly, is how our sun ignited, becoming a brilliant, self-luminous star. Meanwhile, in the outer reaches of the protoplanetary disk, beyond the ice line, the distance where temperatures were high enough to prevent ices from condensing, the icy grains and metallic clumps were constantly colliding and merging. These collisions weren't always gentle. They were often violent, shattering grains and sending fragments flying. Over countless generations, these fragments gradually grew through a process called accretion. Larger clumps attracted smaller ones through gravitational forces, forming progressively larger bodies, planetesimals, and eventually planets. The formation of the terrestrial planets, Mercury, Venus, Earth, and Mars, is thought to have occurred in this outer region, where the abundance of icy materials provided a plentiful supply of building blocks. The gravitational interactions between these planetesimals likely played a crucial role, shaping their orbits and influencing their final compositions. The giant planets, Jupiter and Saturn, formed further out, where the gravitational influence of the Sun was less dominant, allowing them to accumulate vast quantities of gas and dust. These giants are thought to have formed through a process called core accretion, where a dense core of heavier elements eventually triggered the accumulation of gas from the surrounding disk. The final stages of planet formation involved countless collisions and rearrangements. The young solar system was a chaotic place, filled with debris and rogue planetesimals. Gravitational interactions between the planets themselves continued to sculpt their orbits, leading to the current configuration of the planets around the Sun. It's a remarkable story of creation, driven by fundamental forces and shaped by the laws of physics. It's a process that has played out countless times throughout the universe, giving birth to countless solar systems, each with its own unique characteristics and potential for life. And it all began with a rotating cloud of gas and dust, a seed from which our own cosmic neighborhood blossomed. The early history of our inner solar system, the realm of Earth, Mars, and the other rocky planets, wasn't a quiet one. For a significant period, roughly between 4.1 and 3.8 billion years ago, it was experiencing a cosmic barrage unlike anything seen since. Scientists call this the Late Heavy Bombardment, and it's a story etched onto the surfaces of our planet and the red dust of Mars. The evidence for this intense period of impacts is remarkably compelling, largely thanks to the study of meteorites. Remnants of shattered asteroids and comets, found scattered across the globe, and the meticulous analysis of crater densities on planetary surfaces. Initially, the giant planets Jupiter, Saturn, Uranus, and Neptune were much closer to the Sun than they are today. This wasn't always the case. They migrated outwards over billions of years, a process driven by gravitational interactions within the still-forming solar system. This migration wasn't a gentle drift. It was a chaotic dance, a swirling vortex of gravitational forces that dramatically altered the arrangement of the planets. Jupiter and Saturn, being the most massive, played the leading roles in this turbulent movement. As the giant planets shifted, their gravitational pulls began to disrupt the orbits of smaller bodies in the outer solar system, the asteroids and comets. These smaller bodies, initially formed from the same swirling disk of gas and dust that created the planets, were now caught in a cosmic tug-of-war. They weren't simply knocked out of the system entirely. Instead, they were flung inwards, towards the inner solar system. Think of it like a child spinning a ball on a string. As the child moves their hand, the ball doesn't just stop, it's pulled along for the ride. The gravitational influence of Jupiter and Saturn was particularly strong. They were acting like cosmic billiards balls, sending these inner solar system objects careening towards the inner planets. The evidence for this comes from the observation that the oldest surfaces of the Moon and Mars are heavily cratered, bearing witness to a period of intense bombardment. These craters aren't random. They are concentrated in time, corresponding to the period of the Late Heavy Bombardment. Scientists estimate that during this time, the inner solar system experienced an influx of objects at a rate hundreds, perhaps even thousands, of times greater than what we observe today. This wasn't a constant stream. It was episodic, with periods of intense bombardment followed by relative quiet. The exact timing and duration of these periods are still being refined, but the broad time frame remains established. The consequences of this bombardment extended far beyond just surface cratering. The energy released by these collisions was immense, heating the surfaces of the planets and potentially driving away much of the remaining primordial atmosphere. It's believed that the frequent impacts played a significant role in delivering water to the early Earth, though the precise mechanisms are still debated. Perhaps comets, rich in water ice, were targeted by Jupiter's gravitational influence and subsequently delivered their precious cargo. Furthermore, the bombardment likely played a critical role in the delivery of organic molecules, the building blocks of life, to Earth. While the idea of life originating from meteorites is intriguing, the sheer volume of material impacting the planet during the late heavy bombardment suggests that these molecules could have been incorporated into the planet's crust and mantle, potentially contributing to the chemical conditions necessary for life's emergence. It's important to note that the late heavy bombardment wasn't a single catastrophic event. It was a complex and evolving process, influenced by the ever-changing gravitational interactions between the giant planets and the smaller bodies in the solar system. As the giant planets continued their migration, the intensity and timing of the bombardment gradually decreased. The study of meteorites provides invaluable clues to understanding the composition of these impacting bodies. Many meteorites are classified as chondrites, representing some of the most primitive materials in the solar system. Analysis of these meteorites reveals that the impacting objects were largely composed of rock and metal, similar to the building blocks of the planets themselves. However, some meteorites, particularly carbonaceous chondrites, contain significant amounts of organic molecules, highlighting their potential role in delivering the raw materials for life. Interestingly, the late heavy bombardment isn't unique to our solar system. Astronomers have discovered evidence of similar bombardments occurring in other planetary systems as they're being born. This suggests that intense impacts are a common feature of planet formation, a potentially hazardous stage in the development of any planetary system. It's a stark reminder that the early universe was a dynamic and violent place, a cosmic crucible shaping the worlds we see today. The ongoing study of meteorites, coupled with advanced computer simulations of the giant planet migration, is gradually piecing together a more complete picture of the late heavy bombardment and its profound impact on the early history of our solar system. It's a testament to the power of scientific observation and the ability to unravel the secrets of the cosmos, one impact crater at a time. Ultimately, the late heavy bombardment serves as a crucial chapter in the story of the universe, a violent but essential stage in the creation of our planet and the conditions that might have, eventually, led to the emergence of life. It's a reminder that even the most seemingly stable systems can undergo dramatic changes over billions of years, shaped by the invisible forces of gravity and the relentless dance of the cosmos. The journey to understand the universe continues, and our current focus takes us far beyond our own solar system, to a realm of incredible diversity, the exoplanets orbiting distant stars. For decades, the idea of planets beyond our sun was largely theoretical, a beautiful mathematical possibility. Then, with the development of sophisticated telescopes and innovative detection methods, these worlds began to reveal themselves, not as mere points of light, but as potential environments with their own unique characteristics. A particularly exciting area of study is the examination of exoplanet atmospheres, the gaseous layers that surround these distant worlds. These atmospheres are incredibly difficult to study directly. Because exoplanets are so far away, light reflected from their surfaces is extremely faint, often lost in the glare of their host stars. Instead, scientists employ a technique called transit spectroscopy. When a planet passes in front of its star, a transit, some of the star's light shines through the planet's atmosphere before reaching our telescopes. As this starlight travels through the atmosphere, it gets slightly altered. Specific wavelengths of light are absorbed by molecules within the atmosphere, like tiny filters. Think of it like shining a white light through a prism. The white light is broken down into its constituent colors: red, orange, yellow, green, blue, indigo, and violet. Each color is absorbed at a different wavelength. Similarly, when starlight passes through an exoplanet's atmosphere, certain wavelengths are absorbed by molecules like water, methane, carbon dioxide, or oxygen. These absorbed wavelengths are missing from the light that reaches us, creating a unique spectral fingerprint. The pattern of missing wavelengths, the spectrum, tells us a great deal about the composition of the atmosphere. The data collected from transit spectroscopy is analyzed using powerful computers and sophisticated algorithms. Scientists compare the observed spectrum to theoretical models of planetary atmospheres. These models take into account factors like the planet's temperature, size, and distance from its star. The goal is to identify the molecules present in the atmosphere and determine their relative abundances. It's a remarkably complex process, akin to detective work, piecing together clues from a distant world. Currently, several exoplanets have yielded particularly intriguing atmospheric signatures. Hot Jupiters, massive gas giants orbiting very close to their stars, have been particularly fruitful. These planets experience extreme temperatures, and the presence of water vapor, methane, and ammonia is frequently detected. These molecules, while not necessarily indicative of life, could suggest conditions where liquid water might exist under certain circumstances. The detection of methane, for example, is interesting because methane is a relatively unstable gas in an oxygen-rich environment, a combination that could potentially arise from biological activity, although geological processes can also produce it. Moving outwards, planets orbiting within the habitable zone, the region around a star where liquid water could exist on a planet's surface, are receiving intense scrutiny. While direct observation of a planet's surface is impossible at present, the analysis of their atmospheres offers a tantalizing glimpse into their potential. The James Webb Space Telescope, with its unprecedented infrared capabilities, is revolutionizing this field. Its ability to detect faint infrared light allows it to probe the atmospheres of these potentially habitable worlds with unparalleled precision. The detection of water vapor, even in trace amounts, is a critical step. The presence of water is considered a fundamental requirement for life as we understand it. However, simply detecting water vapor is not enough. Scientists also look for other biomarkers, molecules that could provide stronger evidence of biological activity. Oxygen, for instance, is a powerful biomarker, but its presence also depends on ongoing biological processes. Beyond water and oxygen, researchers are investigating the presence of other molecules, such as ozone O3, which is formed by the interaction of oxygen and ultraviolet light. The detection of ozone could suggest the presence of an atmosphere that shields the surface from harmful radiation. Furthermore, studies are being conducted to detect disequilibrium, an imbalance in the abundance of different molecules. For example, a significant amount of methane alongside a substantial amount of oxygen would be a particularly compelling sign, as it would require a constant source of methane production to maintain that balance. The study of exoplanet atmospheres is still in its early stages, and the technology is constantly evolving. Future telescopes, even more powerful than the James Webb Space Telescope, promise to provide even more detailed information. Scientists are developing new techniques, such as direct imaging, which aims to capture images of exoplanets directly, rather than relying on transit spectroscopy. Ultimately, the goal is to find planets with atmospheres that are not just habitable, but potentially inhabited. It's a long and challenging pursuit, requiring collaboration across disciplines: astronomy, chemistry, biology, and geology. Each new discovery brings us closer to answering one of the most fundamental questions in science. Are we alone in the universe? The answers, gleaned from the faint light filtering through the atmospheres of distant worlds, are slowly but surely coming into view. The early solar system wasn't the serene place we see today. It was a chaotic swirl of dust, gas, and icy particles, remnants from the death of a long-gone star. This leftover material, primarily composed of water ice, presented a fundamental puzzle. Where did all this water come from, and how did it find its way to the planets? The prevailing theory suggests a surprising origin, far beyond the immediate vicinity of our sun. Scientists now believe a significant portion of the water within our solar system, and potentially throughout the galaxy, was seeded from the Oort cloud, a vast, icy reservoir located at the very fringes of our solar system. This cloud, stretching out to perhaps a light year from the sun, is populated by trillions of icy bodies, essentially leftover planetesimals from the solar system's formation. These icy fragments, warmed by the young sun's radiation, became a primary source of water delivery. The mechanism for this delivery, known as the late veneer theory, describes a process that unfolded over millions of years. As the sun grew brighter, the inner solar system became increasingly inhospitable to volatile ices like water. However, the outer solar system remained cooler, allowing these ices to persist. Gravitational interactions between the giant planets Jupiter, Saturn, Uranus, and Neptune played a crucial role. These planets, through their immense gravitational pulls, acted like cosmic shepherds, scattering icy bodies from the Oort cloud towards the inner solar system. These weren't gentle nudges, they were powerful, disruptive forces. Imagine a swarm of bees suddenly taking flight, buzzing and swirling around a hive. That's a simplified analogy for what was happening. These encounters, known as gravitational scattering events, flung icy planetesimals, some the size of small moons, inwards. Many of these projectiles never made it to the inner planets, most being deflected by the sun's gravity or flung out of the solar system entirely. However, a considerable number, particularly those impacting the early terrestrial planets, Mercury, Venus, Earth, and Mars, managed to survive the fiery entry into the planet's atmosphere. The late heavy bombardment, a period of intense impacts that occurred roughly 4 billion years ago, was directly linked to this influx of water-bearing debris. While initially conceived as a result of gravitational interactions between the giant planets, the delivery of water significantly amplified this event. The impacts weren't just delivering water, they were also transporting volatile compounds, including methane and ammonia, alongside the water. The sheer volume of material striking the inner planets during this time was staggering. Evidence for this water delivery is found across the inner solar system. Mars, for instance, is remarkably dry today, but ancient Martian rocks contain hydrated minerals that have incorporated water molecules into their crystal structures. These minerals, like clays and sulfates, provide a direct record of past aqueous alteration, indicating significant periods of water exposure. Scientists have identified isotopic signatures in these Martian rocks that match those found in Earth's ocean, further strengthening the link to a common source. Venus, despite its scorching surface temperatures, also exhibits evidence of past water. The discovery of hydrated minerals within Venusian rocks suggests that the planet once had a significantly wetter environment, potentially with extensive oceans, though these were lost to the planet's runaway greenhouse effect. The composition of Venusian rocks, particularly the abundance of magnesium and silicon, indicates a strong connection to water-rich materials delivered during the late heavy bombardment. Earth, of course, is the most obvious recipient of this water delivery. While Earth's early history is complex, with evidence suggesting periods of extensive volcanic activity that may have temporarily lost water to space, the vast majority of our planet's water, roughly 97%, originated from the outer solar system. The isotopic ratios of hydrogen and oxygen in Earth's oceans and atmosphere are remarkably similar to those found in the outer solar system, providing compelling evidence for this shared origin. Beyond Earth and Mars, other bodies in the solar system also show evidence of water delivery. The moons of Jupiter and Saturn, particularly Europa and Enceladus, are now recognized as prime targets in the search for extraterrestrial life. Europa, with its vast subsurface ocean beneath a thick ice shell, and Enceladus, which actively spews water vapor and ice particles from its south polar region, are considered potential habitats due to their access to liquid water, a fundamental requirement for life as we know it. The plumes emanating from Enceladus contain organic molecules and salts, further bolstering the theory that it's a remnant of the outer solar system's watery past. Scientists continue to refine their understanding of this complex process, using sophisticated computer simulations and detailed analyses of meteorites, remnants of the early solar system, to reconstruct the dynamics of water delivery. The discovery of water-rich asteroids, such as those found in the asteroid belt, also provides valuable insights into the distribution of volatile materials within the solar system. Ultimately, the story of water in our solar system is a story of planetary evolution, gravitational interactions, and the enduring legacy of the material that formed our sun and planets. It's a tale that reminds us of the interconnectedness of celestial objects and the remarkable processes that have shaped our world, and perhaps other worlds, into what they are today. It's a story written in the rocks and ice, a silent witness to the birth and evolution of our solar system. The vastness of space holds a question that has captivated humanity for millennia. Are we alone? As our understanding of the universe has grown, fueled by incredible technological advancements, the pursuit of life beyond Earth has transformed from a philosophical musing into a rigorously scientific endeavor. It's a quest built on careful observation, sophisticated analysis, and a growing appreciation for the diverse ways life might arise and thrive. One of the first steps in this search is defining what we mean by habitable. It's not simply about finding a planet with liquid water, although that's undoubtedly crucial. Habitability is a complex tapestry of conditions, including the presence of a suitable star, a stable planetary environment, and most importantly, the availability of the necessary chemical ingredients for life as we know it. We examine planetary systems around different types of stars, red dwarfs, like our sun, or cooler, smaller stars. These stars present unique challenges and opportunities. Red dwarfs are incredibly common, making them prime targets, but their frequent flares, sudden bursts of energy, can be detrimental to surface life, stripping away atmospheres and exposing planets to intense radiation. Conversely, planets orbiting these stars might experience tidal heating, generated by the gravitational tug-of-war with their star, potentially creating internal warmth that could sustain subsurface oceans. The concept of a habitable zone, the region around a star where liquid water could exist on a planet's surface, has been a cornerstone of this research. However, it's now understood that planets outside this traditional zone aren't automatically ruled out. A planet with a sufficiently dense atmosphere, for example, could trap enough heat to maintain liquid water despite receiving less sunlight. Furthermore, the composition of that atmosphere becomes incredibly important. The presence of gases like carbon dioxide and methane, for instance, could create a greenhouse effect, effectively warming the planet. But the search hasn't been limited to planets with potentially habitable surfaces. Increasingly, scientists are focusing on the possibility of life in subsurface oceans. This idea gained significant traction with the discovery of Europa, one of Jupiter's moons, and Enceladus, a moon of Saturn. These icy worlds possess vast, global oceans hidden beneath thick layers of ice. The energy sources for these oceans, tidal heating from their parent planets, radioactive decay within their interiors, create conditions that could potentially support microbial life. Evidence for this potential is compelling. Plumes of water vapor erupting from Enceladus, South Pole, have been directly sampled by the Cassini spacecraft. These plumes contain salts, organic molecules, and even molecular hydrogen, a potential energy source for microbes. The presence of hydrothermal vents on the ocean floor, similar to those found on Earth, further strengthens the argument for habitable conditions. These vents release chemicals from the planet's interior, providing a source of energy and nutrients for life, independent of sunlight. The strategies employed in the search for extraterrestrial life are multifaceted and technologically ambitious. The James Webb Space Telescope, with its unparalleled infrared capabilities, is playing a pivotal role. It's being used to analyze the atmospheres of exoplanets, searching for biosignatures, chemical indicators that could suggest the presence of life. These biosignatures aren't simply detecting oxygen. Researchers are looking for combinations of gases that are unlikely to occur through non-biological processes. Methane, alongside oxygen, is a particularly intriguing combination, as methane is easily destroyed by oxygen. Another exciting approach involves robotic missions designed to explore icy moons like Europa and Enceladus directly. The Europa Clipper, scheduled to launch soon, will conduct multiple flybys of Europa, gathering data about its surface and subsurface. Future missions could even deploy probes to melt through the ice and explore the ocean firsthand. These probes would carry instruments designed to detect signs of life, such as DNA or RNA, and to analyze the chemical composition of the water. Beyond these direct explorations, scientists are also developing techniques for remote detection. Radio telescopes scan the skies for potential signals from intelligent civilizations, the search for extraterrestrial intelligence, or SETI. While the chances of detecting a deliberate signal are slim, the possibility remains a driving force in this endeavor. The search for life beyond Earth isn't just about finding another planet inhabited by aliens. It's fundamentally about understanding our place in the universe. Discovering life elsewhere would revolutionize our understanding of biology, geology, and cosmology. It would demonstrate that life is not a unique phenomenon confined to our small blue planet, but rather a potentially common occurrence throughout the cosmos. Even if we don't find definitive proof of life, the pursuit itself is pushing the boundaries of scientific knowledge and inspiring innovation. The data gathered from these missions will refine our understanding of the conditions necessary for life to emerge and thrive, regardless of whether that life is microbial or something far more complex. Furthermore, the technologies developed for this search, advanced telescopes, robotic probes, and sophisticated analytical instruments, will undoubtedly have broader applications in fields like medicine, materials science, and energy production. Ultimately, the quest to find life beyond Earth is a testament to humanity's innate curiosity and our unwavering desire to explore the unknown. It's a story that is still being written, a story filled with hope, anticipation, and the profound realization that we may not be alone in this vast and wondrous universe. The universe, as we've come to understand it, doesn't just radiate light. It also hums with a secret vibration, a ripple in the very fabric of space and time itself. For centuries, scientists theorized about these ripples, initially predicted by Albert Einstein's theory of general relativity. Einstein had shown us that gravity isn't just a force pulling things together, it's a curvature in space-time. A massive object like a star or a planet warps the space around it, and this warping is what we experience as gravity. But Einstein's theory also predicted that accelerating massive objects could create disturbances, waves, that would travel across the universe at the speed of light. These waves, known as gravitational waves, were faint and incredibly difficult to detect, like trying to hear a drop of water splash in the middle of the ocean from miles away. The challenge lay in the fact that these waves interact with matter incredibly weakly. They stretch and squeeze space itself, but the changes are so minuscule that conventional instruments struggle to register them. For decades, scientists pursued various methods, building increasingly sensitive detectors, but without definitive proof. Then, in 2015, something truly remarkable happened. Two giant observatories, the Laser Interferometer Gravitational Wave Observatory, LIGO, in the United States and Virgo in Italy, announced the first direct detection of gravitational waves. LIGO's detectors were particularly ingenious. They consisted of 4 L-shaped arms, each several kilometers long, arranged in vacuum and cooled to near absolute zero. At each arm's end, a laser beam was split into two, and each beam traveled down one arm before being reflected back to the point where the original beam was split. If a gravitational wave passed through the detector, it would subtly change the length of the arms, stretching one side while squeezing the other, and this would cause a tiny shift in the time it took for the laser beams to return. These minuscule shifts, measured with extreme precision, provided the undeniable evidence of the wave's existence. The first detected gravitational waves came from the merger of two black holes, approximately 29 and 36 times the mass of our Sun. These weren't just any black holes. They were relatively close to Earth, in a galaxy called NGC 4993. The merger itself was a cataclysmic event, two supermassive objects spiraling inwards, accelerating to unimaginable speeds, and then colliding with a breathtaking flash of energy. This wasn't a gentle collision. It was a violent dance of destruction that reshaped the surrounding space-time. The waves generated by this event traveled over 6 billion light-years to reach Earth, a journey that began billions of years before our solar system even formed. The detection of these black hole mergers revolutionized our understanding of these enigmatic objects. Before, black holes were largely theoretical constructs, described by their mass and spin. Now, we could directly observe their formation, the violent process of two black holes combining into a single, more massive black hole. It confirmed that black holes routinely merge, a process that likely contributes significantly to the growth of supermassive black holes found at the centers of galaxies. But the story didn't end there. Soon after the first detection, LIGO and Virgo detected gravitational waves from a different source, the merger of two neutron stars. Neutron stars are incredibly dense remnants of massive stars that have undergone supernova explosions. These objects are far smaller than black holes, but they pack an immense amount of mass into a tiny volume, making them some of the densest objects in the universe. The merger of these neutron stars was an even more spectacular event. The collision released an incredible amount of energy in the form of light, radio waves, and other forms of radiation, an electromagnetic cascade that was observed across the entire spectrum. This simultaneous detection of gravitational waves and electromagnetic radiation from the same event is known as a multi-messenger observation. This opened a new window into the universe, allowing scientists to study events that were previously invisible. It confirmed theoretical models predicting how neutron stars interact and allowed researchers to probe the extreme physics occurring within these objects. Furthermore, the observation provided constraints on the speed of gravity, confirming that it travels at the speed of light, as Einstein predicted. The detection of gravitational waves isn't just about studying black holes and neutron stars. It's about fundamentally changing our understanding of the universe's evolution. By studying the gravitational waves generated by these mergers, scientists can probe the processes that shape the cosmos, learning about the formation of galaxies, the growth of supermassive black holes, and the dynamics of the early universe. Moreover, gravitational wave astronomy is opening up a new era of exploration. Scientists are designing new, more sensitive detectors, including space-based observatories, to listen for gravitational waves from a wider range of sources, from the Big Bang itself to the eventual collapse of massive stars. The universe, it turns out, isn't just seen, it's also heard. The continuing detection of gravitational waves promises to unlock many more secrets about the universe, furthering our understanding of space, time, and the fundamental laws that govern it all. It is a truly remarkable scientific achievement and an exciting step towards a deeper understanding of our place in the cosmos. The universe, as we've begun to understand it, is a place of incredible energy and density, a canvas painted with the echoes of the Big Bang. While we've explored the formation of galaxies and the ripples of gravitational waves, there remain some extraordinarily speculative, yet compelling, ideas about the universe's history, concepts that propose structures far more fundamental than the galaxies themselves. One of these is cosmic string theory, a proposal that suggests the cosmos was once threaded with incredibly thin, immensely dense objects called cosmic strings. These strings aren't like the strings of a musical instrument. They are theoretical entities, remnants from the earliest moments of the universe, predicted by some theories of particle physics. The most common scenario for their creation involves the decay of topological defects, irregularities in the fabric of space-time, that arose during the period of rapid expansion known as inflation, a fraction of a second after the Big Bang. During inflation, the universe expanded exponentially, stretching distances far beyond anything we observe today. This expansion didn't happen uniformly. It created ripples and folds in space-time, much like drawing a wave on a pond. These ripples, if they were of a specific type, could have solidified into these incredibly dense strings. The key property of cosmic strings is their density. They're estimated to be far denser than a neutron star, perhaps even denser than a black hole, although their exact density is still a matter of theoretical investigation. This immense density is crucial to their behavior and potential impact. Because they are so dense, strings warp spacetime around them in a way that's far more pronounced than, say, a galaxy. Think of spacetime as a giant, invisible trampoline. A bowling ball creates a significant dip, but a string, even a very thin one, would create a dramatically deeper and more complex distortion. Now, what exactly do these warped spacetimes do? The most exciting possibility is that these strings could have interacted with each other, creating ripples in spacetime similar to gravitational waves, but with potentially much larger amplitudes and different characteristics. These interactions, known as string-string interactions, wouldn't just generate gravitational waves. They could have created a background hum of gravitational waves across the universe. Scientists have been searching for this primordial gravitational wave background, a faint signal left over from the early universe. And while direct detection remains elusive, it's a tantalizing possibility. The characteristics of these waves, their frequency and amplitude, would depend directly on the properties of the strings themselves, offering a unique fingerprint of the universe's infancy. Furthermore, the intense gravitational fields around these strings could have played a crucial role in the formation of larger structures, like galaxies. The theory proposes that as the universe expanded and cooled, these strings could have acted as gravitational scaffolding, attracting and concentrating matter, dark matter primarily, around them. This process is often described as string-mediated structure formation. Rather than galaxies forming solely through gravitational collapse of ordinary matter, the strings provided a pre-existing gravitational landscape, accelerating the clustering of matter. It's like having a pre-existing framework upon which galaxies could assemble. Another fascinating consequence of these string fields is their potential to generate silk, gravitational waves. These are waves with very short wavelengths, corresponding to the size of the strings themselves. As the universe cooled, these waves would have interacted with the photons, light particles of the early universe, scattering them and effectively smoothing out the density fluctuations. This silk damping had a significant impact on the formation of the first structures. It suppressed the growth of small density perturbations, influencing the final distribution of matter in the cosmos. The study of cosmic strings isn't just about detecting gravitational waves, it's also about understanding the fundamental physics of the early universe. Analyzing the properties of the string network, their density, their interactions, and their effect on light, could provide crucial clues about the energy scale of inflation and the nature of the fields that drove this rapid expansion. It's a way of probing the universe's deepest secrets. Current observational constraints, primarily from gravitational wave detectors like LIGO and Virgo, and from the cosmic microwave background radiation, are putting limits on the properties of cosmic strings. While no definitive evidence has been found to directly confirm their existence, the ongoing search continues. Scientists are looking for specific signatures in gravitational wave data patterns that would distinguish string-string interactions from those produced by other astrophysical events. The search relies on the idea that the early universe was a much more chaotic and energetic place than it appears to us today. Moreover, theoretical advancements are constantly refining the models of string interactions and their impact on structure formation. Researchers are exploring different scenarios, from networks of parallel strings to strings interacting with each other in complex ways. The future of cosmic string research depends on a combination of theoretical development and increasingly sensitive observational capabilities. It's a frontier of cosmology, pushing the boundaries of our understanding of the universe's origin and evolution. Ultimately, the study of cosmic strings represents a bold and ambitious attempt to understand the universe's earliest moments. It's a reminder that our current models, while remarkably successful, are still just approximations of a reality that remains profoundly mysterious. The quest to find evidence for cosmic strings is a testament to the human desire to unravel the universe's greatest puzzles, one gravitational wave, one theoretical insight at a time. The universe, as we've begun to understand it, is truly enormous. We've spent considerable time charting its growth, from the initial moments after the Big Bang, influenced by ripples from cosmic strings and the ever-present potential for gravitational waves to shape its evolution. We've explored the possibilities of life, not just on planets orbiting distant suns, but perhaps thriving in the hidden depths of icy moons or within the intense gravitational fields generated by these massive objects. Yet, as we gaze out into the darkness, a persistent and deeply unsettling question arises. Where is everyone? This is the essence of the Fermi paradox. It's a deceptively simple observation combined with a profound implication. Based on our current understanding of the cosmos, the sheer scale of galaxies, the prevalence of stars, the frequent occurrence of planetary systems, and the established fact of chemical elements necessary for life, it seems statistically almost certain that other civilizations should have arisen. There should have been countless opportunities for life to spark, for intelligence to develop, and for those civilizations to eventually become interstellar travelers, exploring and colonizing the galaxy. The argument, often presented in a stark way, is that given the age of the universe, roughly 13.8 billion years, there's been ample time for civilizations to emerge and spread. The Milky Way galaxy itself contains hundreds of billions of stars, many with planetary systems, and our own galaxy is just one among hundreds of billions of galaxies in the observable universe. The numbers alone suggest a staggering probability of other intelligent life. However, despite this apparent certainty, we've found no evidence. No radio signals, no alien probes, no traces of their presence, nothing. This discrepancy, the contrast between the high probability of extraterrestrial life and the complete lack of contact, is the heart of the paradox. It's not simply a question of are there aliens, but rather, why haven't we detected them? There are numerous proposed solutions, each with its own level of plausibility and potential implications for our own future. One frequently discussed possibility is the Great Filter. This concept suggests that there is some stage in the development of life, intelligence, or civilization that is incredibly difficult, perhaps even insurmountable, for most species to overcome. It could be a catastrophic event, a natural disaster, a self-inflicted crisis, or something we haven't even conceived of yet, that routinely wipes out advanced civilizations before they can achieve interstellar travel. Perhaps the emergence of complex life itself is the filter, or the inevitable development of weapons capable of destroying a species. We don't know, and that's what makes this solution so unsettling. Another, somewhat more optimistic, interpretation involves a dark forest scenario, popularized by the science fiction author Cixin Liu. This theory posits that the universe is a competitive space, and any civilization that reveals its presence risks annihilation by more advanced, potentially hostile neighbors. The reasoning is that broadcasting your location invites attack. Silence is the best defense. Essentially, every civilization chooses to remain hidden, fearful of detection. There's also the possibility that interstellar travel is far more difficult and energy-intensive than we currently assume. Perhaps the distances between stars are simply too vast, the energy requirements too great, or the technological hurdles too significant to overcome. Maybe civilizations exist, but they exist in ways we don't readily recognize, utilizing technologies or dimensions beyond our current comprehension. Furthermore, our search strategies may be flawed. We've primarily focused on detecting radio signals, assuming that any advanced civilization would inevitably use this technology. But it's possible that they communicate through entirely different means, perhaps utilizing neutrino beams, gravitational waves, or other forms of communication that we haven't yet considered. Our methods are limited by our own understanding of physics and technology. It's also conceivable that advanced civilizations have already moved beyond our current understanding of civilization itself. Perhaps they've transcended physical existence, existing in purely informational states, or have evolved into forms unrecognizable to us. The timescale of cosmic events is immense. A few thousand years, from a human perspective, is a minuscule fraction of galactic history. The Fermi paradox isn't a problem with a single, definitive answer. Instead, it's a profound reminder of the limits of our knowledge, the potential vastness of the universe, and the uncertainties surrounding the evolution of life. It forces us to confront fundamental questions about our place in the cosmos and the possible futures of our own civilization. Ultimately, the silence may not be an indication of emptiness, but rather a challenge to expand our perspectives and continue to explore the mysteries that lie hidden within the grand, unfolding story of the universe. The current understanding of the universe suggests a grand, unfolding story, one that stretches far beyond our ability to directly observe its final chapters. We've traced the universe's violent birth, the Big Bang, and witnessed its slow, intricate evolution, marked by the formation of galaxies, stars, and planets. But what lies ahead? The answers, frankly, are profoundly uncertain, colored by the nature of dark energy and our still incomplete knowledge of the cosmos. We're venturing into the realm of cosmological forecasting, attempting to predict the universe's fate based on our current models, which are themselves subject to change. One possibility, and a somewhat unsettling one, is the Big Rip. This scenario stems from the continued acceleration of the universe's expansion, fueled by dark energy. If dark energy isn't just a constant force, but its density increases over time, a currently debated possibility, then the rate of expansion would become increasingly drastic. Imagine galaxies, then solar systems, then planets, tearing themselves apart as the space between them stretches faster and faster. The fabric of spacetime itself would be ripped as the expansion overcomes all binding forces, ultimately reducing everything to its most fundamental constituents, perhaps even individual particles. It's a visually dramatic end, characterized by a violent disintegration rather than a slow fading. The timescale for this event, if it were to occur, is still unknown, but calculations suggest it could happen within tens of billions of years, a truly distant yet terrifying prospect. Another far more familiar sounding fate is the Big Crunch. This scenario posits that the expansion of the universe, currently accelerating, will eventually reverse. Gravity, the force that pulls everything together, would begin to dominate. Galaxies would begin to move closer, colliding with increasing frequency. The universe would contract, becoming hotter and denser with each passing moment. Eventually, everything, all the matter and energy, would collapse into a single, infinitely dense point, an exact reversal of the Big Bang. This isn't a cataclysmic explosion, it's a final implosion, a return to the singularity from which the universe originated. The timescale for a Big Crunch is, again, uncertain, but current data suggests it's a possibility, although the accelerating expansion makes it the less favored outcome. Perhaps the most widely discussed, and perhaps most sobering, cosmological scenario is heat death, also sometimes referred to as the Big Freeze. This outcome arises from the concept of entropy, the tendency of systems to move towards disorder. As the universe expands, energy is gradually dispersed, becoming more evenly distributed. Stars eventually burn out, galaxies drift further apart, and black holes slowly evaporate through Hawking radiation, a process by which they emit particles, gradually losing mass. Over an incredibly long period, the universe will approach a state of maximum entropy, a state of complete thermal equilibrium. There will be no temperature differences, no usable energy, and no processes occurring. It's a cold, dark, and utterly lifeless end, not an explosion or a contraction, but a state of complete stagnation. However, the current evidence overwhelmingly points to a scenario driven primarily by dark energy. Observations of distant supernovae have provided the strongest evidence for this accelerating expansion. We now believe that dark energy constitutes approximately 68% of the universe's total energy density. This constant and ever-increasing expansion is pushing galaxies apart at an accelerating rate. The implications are profound. The universe isn't destined to collapse. It's destined to keep expanding indefinitely. The fate of the solar system within this expanding universe is particularly intriguing. Our sun will eventually expand into a red giant, engulfing Mercury and Venus. Earth will likely be vaporized as the sun grows. But even after that, the universe will continue to expand, carrying the remnants of our solar system, perhaps just a cloud of dust and gas, further and further away from any potential future observers. The distances between galaxies will grow so vast that communication will become impossible. The ongoing expansion isn't simply about distant galaxies drifting away. It affects the very fabric of space-time. The wavelengths of light emitted by distant objects are stretched, redshifted, as the universe expands, a phenomenon known as cosmological redshift. The further away an object is, the greater the redshift, providing a crucial tool for measuring distances in the cosmos. It's a continual reminder of the universe's dynamic nature. Scientists are actively researching the nature of dark energy, attempting to understand what's driving this relentless expansion. Is it a cosmological constant, an inherent property of space itself? Or is it something more complex, something that changes over time? Perhaps dark energy is connected to inflation, the incredibly rapid expansion that occurred in the very early universe. The answers remain elusive, and the future of the universe hinges on unlocking these mysteries. Ultimately, the story of the universe's future is a story of immense timescales, billions and even trillions of years. It's a story of stretching space, diminishing energy, and the gradual fading of all things. While the Big Crunch and Big Rip offer dramatic and unsettling possibilities, the prevailing evidence leans toward a universe continuing to expand forever, culminating in a state of heat death. It's a humbling thought, a reminder of our place in the grand scheme of things, and a testament to the power of scientific inquiry to grapple with the most profound questions about existence. It's a story still being written, one observation, one calculation at a time. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. The story of the universe has unfolded, revealing its vastness and ancient beauty. Let your thoughts drift now, calm and unhurried, like stardust settling into quiet darkness.